small water drops generally stick to solids, as we already discussed. This is a key factor in the contamination of surfaces by mineral particles or microorganisms which can grow within water. In addition, sticking drops distort or even cancel the transparency of a glass. In order to avoid this situation, we can try to render the surface as hydrophobic as possible. An appropriate choice of chemical composition, a coating of fluorinated polymers, for instance, increases the contact angle of water up to typically 120 degrees. But using chemistry only makes it impossible to reach higher angles, letting us far from the ultimate value of 180 degrees. However, a large number of leaves, such as the one of lotus or ginkgo biloba, and many insects have surfaces such that water forms pearls on them. This super hydrophobic character makes drops highly mobile, which prevents contamination and favors the evacuation of water at the surface. We shall discuss in this module the origin of superhydrophobicity and present some spectacular dynamic properties of this state. So, the first question is, how can we generate water pearls? Well, as often, we start from Young's equation, this equation that fixes the contact angle of a liquid on a solid. So if I sketch a solid like this, I place some liquid at a small scale. We learn from Thomas Young that the contact angle, or to be more precise, the cosine of the contact angle, is given by the difference between surface tension between solid and air minus surface tension between solid and liquid divided by the surface tension of the liquid. When we look at this equation, we can notice a very interesting limit, which is the case when the solid is, so to speak, vapor or air-like. So if S, the index for the solid, becomes A for air, then we get cosine theta is gamma AA, which is nothing, minus gamma AL, which is exactly gamma LA at the denominator. And so we get, for this cosine, -1, which means that in such a case, the contact angle tends towards its ultimate value, 180 degrees. So this is exactly our definition of a water pearl. And if we sketch naively such an object, we have something which is very peculiar, like this, a sphere sitting on a solid, and we guess immediately that this object should be extremely mobile, first because we suppress the contact between the solid and the liquid, and second because we also suppress contact lines, and we know that most of the dissipation, viscous dissipation in particular, takes place close to contact lines. So then the question is, how can we achieve a solid which is air-like? We have two possibilities. The first one is to have hydrophobic textures at the solid surface. And the second one, which is very different, is to heat this solid at a very large temperature so that vapor comes between the liquid and the solid. And again, we have a solid which is vapor-like. So in this module, we are going to discuss successively these two cases. A key experiment for understanding the superhydrophobic state consists in depositing a water drop on a material covered by micrometric pillars. These pillars are themselves coated by a monolayer of hydrophobic silanes, making Young's contact angle locally larger than 90 degrees. This material is colored owing to the regularity of the structures that decompose white light, generating what is called structural colors, such as the one seen sometimes on the wings of butterflies. When the drop sits on these textures, it is close to be spherical. The intrinsic value of the contact angle has jumped from Young's value, just obtuse, to a value close to 180 degrees. Hence, this experiment demonstrates that microtextures amplify hydrophobicity, making it possible to reach a state that chemistry alone would not generate. So, how can we understand that textures enhance hydrophobicity? For the sake of simplicity, we are going to consider that the solid surface is covered with hydrophobic pillars. And these pillars are taken, let's say, cylindrical. And so we have a surface like this, and saying that this surface is hydrophobic means that locally the contact angle, the one calculated by Young, is obtuse, larger than 90 degrees. So when the liquid is coming, for instance as a drop, very generally it will stay at the tops of the pillars because precisely these pillars are hydrophobic. And so we have the liquid there. And the first thing to notice, of course, is that air is trapped inside the texture. Two questions. The first one is this state possible and why? And the second question is, if we achieve something like that, what is the resulting contact angle? The first question is very easy to answer if we look carefully at these regions, and we have many regions of this type, where solid, liquid, and air are coexisting. If we make a zoom on this region, we have the top of the pillar, and then the side of the pillar, which are like this, and we have to place a contact line. And we can see that there is always a possibility for the contact line to find a position such that locally we have a contact angle which is larger than 90 degrees. This contact angle, which is fixed by the fact that the texture is hydrophobic. This is something very important because it tells us that the design of the solid matters. If we had something very smooth like this, we could not pin the contact lines on such a texture. And so we need, well, let's say angular texture so that we can stop all these contact lines when the liquid meets the solid. Once we understand this point, then we can calculate the resulting apparent contact line. And for that, we do something we did earlier. We consider that the drop is coming to the solid, and then it spreads a little bit until it finds its equilibrium position. The way it does that is to have its edge, which is, let's say, there, and here I assume any angle. I don't know this angle. His name is theta star, and we consider, let's say, the last jump of the drop to find its equilibrium position. And so this little jump is there, and it is defined by some quantity here, which I call dx. And we are going to look at the variation of surface energy arising from this little jump. So dE, which is written per unit length in the direction perpendicular to the blackboard, is, first thing, we create a new interface between solid and liquid, and we suppressed interface between solid and air. And we did that on a proportion of solid, which is the density of pillars, which we call phi. And so phi dx is the quantity to be considered. The second thing is that we create a new interface between liquid and air, which is related to the fact that we assume that the liquid stops at the pillar tops. And there is a price for that, which is gamma LA times 1 minus phi dx. And finally, we have a term we had already in Young's equation, which is related to the fact that when a drop is spreading, its interface between liquid and air, outside interface, is increasing. And it increases by a quantity which is cosine theta star dx. The drop will explore the solid until it reaches the minimum of the surface energy. So when dE is 0, when we are in the well of surface energy. And from that, we can deduce theta star, or more precisely, its cosine. Cosine theta star, as you can see, is something sensitive to the density of pillars multiplied by a quantity where we can introduce cosine theta using Young's relationship. So the first term is phi cosine theta minus 1 plus phi. So this relationship is sometimes called Cassie equation because the state where a liquid sits on the tops of pillars or structures more generally is called the Cassie state. If we look at this relationship, we can notice different interesting things. So the first case is when phi, the density of pillars, becomes 1. Well, in such a case, we are back to a flat substrate, and we get, very logically, that theta star equals theta. We are back to the Young's equation. But here, we are in a situation where phi is a small quantity, small compared to unity, and in this case, we see that cosine theta star is minus 1 plus a correction which is proportional to phi. So this means that we approach the ultimate limit of contact angle, which is 180 degrees, but we never reach this limit because, well, we are sensitive to the fact that we still have some solid beneath the drop, and this correction is just proportional to phi. This is a very interesting fact because it means that if we measure theta star, we can deduce the phi we have, and well, for pillars it's a known quantity, but if you imagine a pearl on a lotus leaf, for instance, we don't know exactly what is the actual contact between the water and the leaf, and this relationship tells us that it should be in principle deduced. The second thing we can notice, of course, if we want to go very close to 180 degrees, we need to make phi as small as possible, and this is something which is possible, but of course there is a limit for that. If phi is too small, well, the drop cannot stay at the top of the textures, and it should fall inside the texture, a very different state, which is called the Wenzel state. For instance, when we deposit water on the leaf of a ginkgo biloba tree, we also obtain pearls that betray the existence of micrometric bumps at the surface. In addition, we observe a major and logical consequence of the drop sphericity, that is, the ability of water to roll off easily even at small tilt of the leaf. This property arises from the conjunction of high contact angle, that is, low contact area, with small angle hysteresis owing to the presence of air beneath the drop on which water cannot stick.
We saw that the contact angle of water on textures is all the larger since the density of textures is smaller. However, we cannot imagine a large drop sitting on a single pillar, and we understand that water on dilute pillars might be in a fragile Cassie state that is likely to impale in the texture, another possible state called the Wenzel state. In the experiment we did earlier, if we give an impulse to the material, we indeed obtain a completely different drop configuration. This corresponds to the transition from the Cassie state to the Wenzel state, permitted by the kinetic energy associated with the impact. We have seen that we can support a drop on top of pillars in the so-called Cassie state, but we have also seen that this state might be destabilized so that the drop impales on the pillars in the so-called Wenzel state. So now we would like to understand how the Cassie state is stable. In order to do so, we will compute the difference in surface energy between the two states. I'm sketching here the substrate which is made of pillars. And these pillars are with a surface fraction phi. This is the fraction of pillars. And since the substrate is rough, I will characterize this roughness by a parameter which is called R, which is the ratio between the actual area of the interface and the projected area. So this is the actual area divided by the projected area. Now, in the Wenzel state, which I will sketch here, the liquid has invaded the space between the pillars, so I have liquid everywhere. Conversely, in the Cassie state, I'm sketching the same substrate here. The liquid is on top of the pillars here. And I will compute the difference in energy when I go from the Wenzel state to the Cassie state. So I'm computing delta E going from Wenzel to Cassie. When I do this, you can see that I'm starting in the space between the pillars from a surface which is wetted by the liquid to a surface which is covered by the gas. So the difference in energy is the area of the space between the pillars, which is the roughness R minus phi. I'm removing liquid, so I have a minus gamma times solid liquid, and I'm adding gas, so to speak, on the substrate, plus gamma solid gas. But in this transformation, I'm also creating a liquid-air interface between the pillars. So I'm adding an energy which is proportional to the interfacial tension between liquid and gas, gamma, multiplied by the fraction between the pillars, which is 1 minus phi. So this is my difference in energy, delta E. Now, I have to consider that the substrate is characterized at the microscopic level by a contact angle theta, which is such that gamma times cosine theta is equal to gamma solid gas minus gamma solid liquid, which is just Young's relation for this material. So I can rewrite my change in energy as delta E equals gamma times 1 minus phi plus R minus phi times cosine theta. I will now use this relation in a situation where the density of pillars is small. So I'm making the hypothesis that phi is much smaller than 1, so I have just a few pillars on the surface. So when phi is much smaller than 1, the difference of energies, delta E, can be written as gamma multiplied by 1 plus R, the roughness coefficient, multiplied by the cosine of the contact angle theta. Now, in order for the Cassie state to be more stable than the Wenzel state, this difference in energy has to be negative. So a condition for stability of the Cassie state is R cosine theta less than minus 1. So in order for this relation to be valid, considering that R is larger than 1, implies that cosine theta must be smaller than 0, implying that the contact angle on the material should be larger than 90 degrees. That is, the material needs to be hydrophobic. And then, in addition, R must be large enough, that is to say larger than 1, but it can vary depending on cosine theta. For example, when the contact angle theta is equal to 120 degrees, the cosine of this angle is minus 1/2. And if R is just larger than 2, then the Cassie state is stable. So we can understand that when we have an hydrophobic material, by making it rough, we favor the Cassie state. Now we would like just to examine two limiting cases. The first one is when the roughness of the substrate goes to 0. In other words, when the substrate is flat. For a flat substrate, of course, the Cassie state does not exist, and we have always a Wenzel state. Now, the other limit, of course, is when the roughness of the substrate is extremely large, that is, when R goes to infinity. And in this case, as soon as cosine theta is negative, that is, as soon as theta is larger than 90 degrees, we will always favor the Cassie state. So in order to fabricate superhydrophobic substrates, we need to have very rough surfaces. A final remark on this result. We have determined the condition for the absolute stability of the Cassie state, but we need to be aware that this state can exist in situations where this condition is not exactly fulfilled. However, in this case, the Cassie state, of course, is only metastable. The sphericity of pearl drops make them amazingly quicker than usual drops. Their adhesion is highly reduced, and the friction is also much smaller than usually, so that water can move typically 100 times faster than on more common solids. In this experiment, recorded at 18,000 frames per second, you can see a drop running down a superhydrophobic material. Its speed rapidly reaches values as high as a few meters per second. In addition, if particles have been first sprinkled at the solid surface, we observe that the quick drop takes these particles with it, a kind of self-cleaning effect, often referred to as the lotus effect. Rain alone is sufficient to clean the material. It is interesting to notice that particles most often adhere to the surface of water, since they decrease its surface energy. Hence, in this experiment, we must not be surprised by the ability of drops to sweep the particles, the main original effect here being the mobility of water. The most spectacular property of superhydrophobic materials might be their ability to reflect impinging drops, a phenomenon called water repellency. In this experiment, we observe many raindrops hitting a repellent material. High-speed imaging allows us to distinguish the spreading and recoiling of each drop at impact. They behave as springs. Kinetic energy can be stored in surface energy with a negligible viscous dissipation, so that the surface energy can be converted back into kinetic energy, allowing the drops to take off. It is also clear in the movie that the time spent on the material at impact depends on drop size. The smaller the drop, the quicker the rebound, which can be seen as a direct evidence of a spring-type behavior, where the response time is known to vary as the square root of the spring mass. And the stiffness of the spring is just surface tension, making the analogy consistent.
While it is rather easy to repel rain, it is much more challenging to repel dew. In this first movie, you can see the condensation of atmospheric water on a cold, superhydrophobic material. The nuclei of water have a micrometric size comparable to that of the texture on the solid, so that these tiny droplets are strongly anchored within the texture. This is particularly obvious when two neighboring droplets coalesce and even more at the end of the movie where we see the strong deformation of the pinned contact line. However, the situation is markedly different on nanometric, dense arrays of hydrophobic cones, such as observed on the wings of cicadas. Because of the geometry and the small size of the texture, even tiny droplets can escape the cavities and keep their mobility. Hence, two coalescing droplets are readily expelled, being able to transfer their surface energy into kinetic energy. They jump at a velocity as high as 1 meter per second, but this velocity is not monotonic with the drop size. Large drops are slowed down by their inertia, while small ones lose energy by viscosity. The optimal ejection is observed around 5 microns in size.
Saying that a material repels water is equivalent to say that it attracts air when immersed in water. Superhydrophobic solids are superaerophilic. This property is exploited in nature, for instance by insects called Notonectae that sometimes plunge in water to escape predators. They can survive at least 15 minutes owing to the plastron of air coating them when submerged. In this experiment, an air bubble rises in water until it meets a superhydrophobic material. Soon after the contact, we see that air spreads on the solid as a wetting drop would do, yet upside down. However, the low value of the gas viscosity makes the dynamics of wetting much quicker in the superaerophilic situation, where the main force opposing spreading is the inertia of the surrounding water.
Many insects or spiders are partly covered in hydrophobic texture, but the case of the spider Argyrineta equita deserves a special discussion. This centimeter-sized spider strictly lives underwater, which forces it to build immersed reservoirs of oxygen. The spider, whose abdomen is superhydrophobic as seen from its silvery aspect, first moves to the surface of the pond, from which it quickly dives, thus capturing a large air bubble on its body. Deeper, the spider gradually builds a nest of air by gently incorporating these bubbles inside a larger cavity anchored by plants and its own web. Contrasting with its behavior at the surface of the pond, the spider slowly leaves its nest, which minimizes the quantity covering its abdomen. This is one case where the combination of superhydrophobicity and dynamics allows one to tune air entrainment in a very efficient way.